Okay, this is our first recording for chapter 2. This is going to cover 2.1 and 2.2. From this point on, all the recordings should cover 2 sections at a time. There might be an exception where maybe only 1 section will be covered in a recording. In this first section, we're going to talk about the tangent line to the curve and average velocity. And actually, average velocity, as we shrink the size of the interval, is going to represent instantaneous velocity. But we're not quite there yet. Let's not get ahead of the game. So we're going to use this position function minus 16t squared plus 192t to represent the position of a moving object. So let's say for the argument here that t is the time in seconds and that p of t is the position in feet. So our average velocities are going to be in feet per second. Notice that right next to the average velocity, I have what's called the difference quotient. It's p of t plus h minus p of t divided by h. Now, in the textbook, there are some nice pictures of what we mean by average velocity, much better than I could certainly draw on this whiteboard. And by the way, I'm using this handheld whiteboard because it's easier to use than trying to use the tablet that integrates with Zoom. I have a writing tablet, but it's very tedious to use. So on page 81, there are some nice drawings in the book of what we mean by average velocity. Notice that we are calculating only the slope of the secant line here. Reminding you what a secant line is, it's a line that passes through a curve in 2 points. Now, by a curve, in this case here, I've chosen for the position of a moving object a nice, friendly quadratic function. You're going to recognize this as a parabola. So let me show you this on my calculator. And by the way, while I am doing this, you should all have TI graphing calculators. Okay. I mean, you don't necessarily absolutely have to have a TI, but that's what I'm using. And that's recommended for the course. So let me bring this up. Give me a minute to adjust the window here. All right, I'm playing around with the window. Give me 1 second. Be patient. Okay, and once again, I will show you for this function that I've chosen, the negative 16t squared plus 192t, to represent the position of an object. Now, what I'm going to do, h is the width of the interval. So I'm going to start off by calculating average velocities over different intervals, except I'm going to cut right to the chase here. In the book, they make it very long process, okay, where they use 7 or 8 different intervals. So I'm going to make this first from t equals 2 to t equals 3. And then I'm going to make it from t equals 2 to t equals 2.1, I believe. Let me check. Yeah, 2.1. And then from t equals 2 to t equals 2.01. And then I'm going to shrink the interval down really small from t equals 2 to t equals 2.001. So what this means is, and I'll show you this in a second, I'll try to make this as close to a lecture as possible, is that for the first interval from 2 to 3, h is 1 second. From 2 to 2.1, h is 1/10 of a second. From 2 to 2.01, h is 100th of a second, and so on and so forth. To come up with these numbers to calculate the average velocity, you're going to rely on your calculator. Now, I'm going to emphasize that on exams, you can use your calculators to check your answers and to make calculations like this, but obviously your calculator is not going to do work for you. And on an exam, you must show all your work or you get no credit. So let me calculate a couple of these for you. So it's P of 3. So it's P of 3 minus P of 2 divided by 3 minus 2. And that gives me 112 feet per second. Now that's not very accurate because the interval is 1 second, a whole 1 second wide. Okay. But as I shrink that interval down, the approximation for the average velocity is going to get closer and closer to the slope of the tangent line. And the slope of the tangent line is going to tell us the instantaneous velocity. So based on that calculation and you using your calculator to make those calculations there, and you can find P of 3 by plugging 3 into the calculator, then by plugging 2 into the calculator for that function and dividing by 1 second. So as I do each of these, my numbers are going to get closer and closer to the slope of a tangent line. So it's going to go from 112 to 126.4 feet per second. And then 127.84 feet per second. And then 127.98 feet per second. And therefore, my guess is going to be 128 feet per second. Now, when I say it's a guess, it's an educated guess, based on the fact that I'm guessing that 128 is the limit when the value of h gets very, very small. Okay? So I'm guessing that the speed of this object or the velocity of this object in feet per second, right at 2 seconds, by the way, because that's what we're squeezing down here. We're squeezing down to the point of pivot at 2 seconds, is that it's traveling at 128 feet per second. You're not going to know this for sure until we actually learn how to take derivatives, but that's the guess. All right, now what I'm going to do here is pause this for a second. Okay, recording again. So that technique for guessing at what the instantaneous velocity of a moving object is can be used for any function. So I'm only going through that one example because that can be applied to any other functions that you're given that represents a moving object and the position of a moving object in time. In the next section, which is 2.2, we're actually going to address limits even more closely. And there are three techniques for evaluating a limit. So let's take a look at this function. Function being that we're going to look for the limit as x approaches 4 of x squared minus x minus 12 divided by x minus 4. The concept of a limit means that we would like to know as x approaches 4 from either side, by the way, either from the left or the right, and we'll talk about one-sided limits later on, but as x approaches 4 from either side, as it gets closer and closer to 4, what does the functional value get close to? It doesn't necessarily mean what is the functional value at 4, because as you can see right here, when we try to substitute x equals 4 into the function, notice that we cannot substitute x equals 4 because it would mean that we would have to divide by 0. And that is an undefined process. So we can't substitute here. By the way, substitution is the primary method for evaluating a limit if you can actually substitute, which in this case, we can't. So therefore, we're going to take another approach. We're going to take a numerical approach. Now, what I'm going to do here also, I'm going to rely on my calculator again, because this is going to be your main tool for technology in this class. Although there is other software that you can use, like Wolfram Alpha, this is your primary source of technology, both on your exams and in doing your labs. Take a look at this. Give me a second to adjust this window here. And this is what the graph of this function looks like. Okay. Yeah, sure. It looks like a straight line. But we know that this function, the one that I just gave you here, by the way, is not defined at x equals 4. It's defined everywhere else, but it's not defined at x equals 4. So we can't just evaluate this limit by substituting. First method is we're going to use then a numerical method. That means we're going to choose values approaching 4 from both sides. So let me show you tables here. We're going to go 3, 3.9, and 3.99. And then coming in from the other side, it's going to be 4.01, 4.1, and 5. So notice what I've done here is I'm squeezing or walking towards the number 4, coming in from both sides, coming in from the left and coming in from the right. And once again, I'm just going to use my calculator to find me these values, f of 3, f of 3.99, f of 3.99, and so on and so forth. So what I'm going to write over here on across from these are the numbers that my calculator is going to give me. First one is going to be 6, then 6.9, then 6.99. And coming in from the other direction, it's going to be 8, and 7.1 and 7.01. And I'm going to guess here that the limit is 7. This is a numerical approach, by the way. Your second method for evaluating a limit. You're going to have to know all of these, by the way. Direct substitution, very rarely are you going to see a function that you can just find the limit by direct substitution, because that's too easy. Okay, so notice that as we squeeze in towards 4 from either side, it looks like the functional values are headed for 7. So therefore, 7 is the limit of this function as we approach 4 from both sides. Okay. Notice one more thing, that the values have to be the same coming in from both sides. In other words, on one side it's headed for 7, on the other side it's headed for 7, so therefore 7 is the limit. If these were headed for different numbers, the limit wouldn't exist. And yes, it can and will be possible sometimes for the limit not to exist. All right, let me erase this and let me go to the last method. And the nice thing about this function that I've chosen, as I can use this to demonstrate all of my techniques. Okay, so what I'm going to do is I'm going to take this function and I'm going to factor the numerator. So this last method requires some algebra. And there are going to be different algebraic techniques. This one is the easiest, which is just factoring. So I'm going to take the limit as x approaches 4 of x minus 4 times x plus 3 divided by x minus 4. And of course, notice what happens here. So I factored the numerator. Notice that the x minus 4 is canceled, and it leaves me with just x plus 3. So now I'm going to take the limit as x approaches 4 of just x plus 3. Now notice that I really haven't changed the function. I've just algebraically rearranged the way that it looks. The limit as x approaches 4 of x plus 3. Now you can substitute x equals 4 into the function. So this is the substitution method. And so 4 plus 3 is equal to 7. And by the way, that now confirms that our answer from the first method, which was the numerical approach, is correct, which means that the limit actually is 7. Now, what does this mean about the graph of the function that I just showed you on the calculator? Well, it means that what looks like a continuous straight line really is not a continuous straight line. It means that there's a hole in that line, a little pinprick of a hole. Where is the hole? The hole is at 4 and 7. So there's a hole at the point 4, 7. So in this video, I've actually taken into account a lot of things. (2.1), we talked about velocities, where we're using a numerical method. We're also using the concept of a limit. Here I'm talking strictly about limits, and I'm taking an example where I used a numerical approach first. I got 7 for the limit. I then used this algebraic method, and I got 7 as the limit. And then I can verify by substituting that the limit actually is 7. And that means that there's a hole in this function at 4, 7. That is 4, 7 being the X and the Y coordinates. So this concludes an introductory video covering 2.1 and 2.2. These, by the way, are mandatory that you watch these, okay? They are, even though this is an online class, this is not a lecture that you have to show up for at a particular time, but it is a lecture that you have to watch. In the chapter review documents that I posted in Blackboard for this course, the chapter review documents also have some other YouTube videos that you can watch that address these same issues. They're a little more professionally made than this, but you should watch them as well. Anything that will help you. So I'm going to stop this recording now. When you get to this and you find this, it'll be in your cloud recordings under Math 214, chapter 2.1 and 2.2. Okay.